In this tutorial, you are going to learn how to do word embeddings with Tensorflow 2.0. If you don't know what that means, don't worry. I'm going to explain what it is and why it's important as we go along. Let's get started. Before we begin with our imports, a couple of housekeeping items. First of all, I am basically working through the Tensorflow tutorial from their website, so I'm going to link that in the description. So I'm not claiming this code as my own, although I do some cleaning up at the end to kind of make it my own, but in general, it's not really my code. Second, if you want to learn how to turn deep learning papers into code, you should check out my new course, Deep Q Learning from Paper to Code. Link in the pinned comment and description. It's on sale for the next 5 days at the $10 price point. Let's get to it. So we start with our imports as usual. We need I/O to handle dumping the word embeddings to a file so that we can visualize later. We'll need matplotlib to handle plotting. We will need TensorFlow as TF, and just a word. So this is TensorFlow 2.1.0 RC1, release candidate 1. So this is, as far as I'm aware, the latest build. So TensorFlow 2.0 throws some really weird warnings, and 2.1 seems to deal with that, so I've upgraded. So if you're running TensorFlow 2.0 and you get funny errors, funny warnings, but you still get functional code and learning, that is why you want to update to the newest version of TensorFlow. Of course, we need Keras to handle pretty much everything. We also need the layers for our embedding and dense layers. And we're also going to use the TensorFlow datasets. So I'm not going to have you download your own dataset. We're going to use the IMDb movie dataset for this particular tutorial. So of course, that is an additional dependency for this tutorial. So now that we've handled our imports, let's talk a little bit about what word embeddings are. So how can you represent a word for a machine? And more importantly, instead of a string of characters, how can you represent a collection of words, a bag of words, if you will? So you have a number of options. One way is to take the entire set of all the words that you have in your, say, movie reviews. You just take all the words and find all the unique words, and that becomes your dictionary. And you can represent that as a one-hot encoding. So if you have, let's say, 10,000 words, then you would have a vector for each word with 10,000 elements, which are predominantly zeros, except for the one corresponding to whichever word it is. The problem with this encoding is that while it does work, it is incredibly inefficient, and because it is sparse. The majority of the data is zero, and there only is one important bit in the whole thing, so not very efficient. And another option is to do integer encoding. So you can just rank order the numbers, the words. You could do it in alphabetical order. The order doesn't really matter. You can just assign a number to each unique word. And then every time that word appears in a review, you would have that integer in an array. So you end up with a set of variable length arrays where the length of the array corresponds to the number of words in the review, and the members of the array correspond to the words that appear within that review. Now this works, this is far more efficient, but it's still not quite ideal, right? So it doesn't tell you anything about the relationships between the words. So if you think of the word, let's say king, it has a number of connotations, right? A king is a man, for one, so there's some relationship between a king and a man. A king has power, right? He has control over a domain, a kingdom. So there's also the connotation of owning land and having control over that land. A king may also have a queen, so it has some sort of relationship to a queen as well. It may have a prince, a princess, all these kinds of different relationships between words that are not incorporated into the integer encoding of our dictionary. The reason is that the integer encoding of our dictionary forms a basis in some higher dimensional space, but all of those vectors are orthogonal. So if you take their dot product, they are essentially at right angles to each other in a hyperdimensional space, and so their dot product is 0. So there's no projection of one vector, one word onto another. There's no overlap in the meaning between the words. At least in this higher dimensional space. Now, word embeddings fix this problem by keeping the integer encoding, but then doing a transformation to a totally different space. So we introduce a new space of a vector of some arbitrary length. It's a hyperparameter of your model, much like the number of neurons in a dense layer is a hyperparameter of your model. The length of the embedding layer is a hyperparameter, and we'll just say it's 8. So the word king then has 8 floating point elements that describe its relationship to all the other vectors in that space. And so what that allows you to do is to take dot products between two arbitrary words in your dictionary, and you get non-zero components. And so what that means in practical terms is that you get a sort of semantic relationship between words that emerges as a consequence of training your model. So the way it works in practice is we're going to have a whole bunch of reviews from the IMDb dataset, and they will have some classification as a good or bad review. So for instance, for the Star Wars Last Jedi movie, I don't think it's in there, but my review would be that it was terrible, awful, no good, totally ruined Luke's character. And so you would see, and I'm not alone in that, so if you did a huge number of reviews for The Last Jedi, you would see a strong correlation of words such as horrible, bad, wooden characters, Mary Sue, things like that. And so the model would then take those words, run them through the embedding layer, and try to come up with a prediction for whether or not that is a good or bad review, and match it up to the training label, and then do back propagation to vary those weights in that embedding layer. So say 8 elements. And by training over the dataset multiple times, you can refine these weights such that you are able to predict whether or not a review is positive or negative about a particular movie, but also it shows you the relationship between the words because the model learns the correlations between words within reviews that give it either a positive or negative context. So that is word embeddings in a nutshell, and we're going to go ahead and get started coding that. So the first thing we're going to have is an embedding layer. And this is just going to be for illustration purposes. And that'll be layers.embedding. And let's say there's 1,005 elements. So we'll say result equals embedding layer TF constant 1, 2, 3. So then let's print the result dot numpy. Okay, so let's head to the terminal and execute this and see precisely what we get. Actually, let's do this too. Print result dot numpy.shape. I think that should work. Let's see what we get in the terminal, and let's head to the terminal now. All right, let's give it a try. Okay, so what's important here is you see that you get an array of 3 elements, right? Because we did the TF constant of 1, 2, and 3. And you see we have 5 elements because we have broken the integers into some components in that 5 element space. Okay, so, and it has shape 3 by 5, which you would expect because you're passing in 3 elements. And each of these 3 elements, these 3 integers, correspond to a word of an embedding layer of 5 elements. Okay, that's relatively clear. Let's go back to the code editor and see what else we can build with this. Okay, so let's go ahead and just kind of comment out all this stuff because we don't need it anymore. So now let's get to the business of actually loading our data set and doing interesting things with it. So we want to use the dataset load function. So we'll say train data, test data, and some info, tfds.load, IMDb reviews / subwords 8K. And then we will define a split, and that is tfds.split.train, tfds.split.test. And we will have a couple other parameters with info equals true. That incorporates information about the data set, and as supervised equals true. So as supervised tells the dataset loader that we want to get back information in the form of data and label as a tuple. So we have the labels for training of our data. So now we're going to need an encoder. So we'll say info.features text.encoder. And so let's just find out what words we have in our dictionary from this. We'll say print encoder subwords first 20 elements. Save that and head back to the terminal and print it out and see what we can see. So let's run that again. And it's hard to see. Let me move my face over for a moment, and you can see that we get a list of words, the underscore. So the underscore corresponds to a space. You get commas, periods, a underscore, and underscore of. So you have a whole bunch of words with underscores that indicate that they are spaces. Okay, so this is kind of the makings of a dictionary. So let's head back to the code editor and continue building on this. So we no longer need that print statement. Now, the next problem we have to deal with is the fact that these reviews are all different lengths, right? So we don't have an identical length for each of the reviews, and so when we load up elements into a matrix, let's say, they're going to have different lengths, and that is kind of problematic. So the way we deal with that is by adding padding. So we find the length of the longest review, and then for every review that is shorter than that, we append a bunch of zeros to the end in our bag of words. So a list of words, you know, the list of integers, we will append a bunch of zeros at the end. So 0 isn't a word. It doesn't correspond to anything. The words start with 1. The rank ordinal numbers start with 1. And so we insert a 0 because it doesn't correspond to anything. It won't hurt the training of our model. So we need something called padded shapes. And that has this shape. So batch size and an empty list, an empty tuple there. So now that we have our padded shapes, we're ready to go ahead and get our training and test batches, so let's do that. And since we are good data scientists, we want to do a shuffle. We're going to use a batch size of 10 and a padded shapes specified by what we just defined. Let's clean that up and let's copy, because the test batches are pretty much identical, except it's test data.shuffle, and it's the same size, so we don't have to do any changes there. Scroll down so you can see. Okay, so that gives us our data. So what we need next after the data is an actual model. So let's go ahead and define a model. So as is typical for Keras, it is a sequential model, and that takes a list of layers. So the first layer is an embedding layer, and that takes encoder.vocab size. Now this is, given to us up here by the encoder object that's given by the information from our data set. And we have some vocabulary size, so there's 10,000 words. Vocabulary size is vocab size. It's just the size of our dictionary. And we want to define an embedding dim. So that's the number of dimensions for our embedding layer. So we'll call it something like 16 to start. So let's add another layer. Global average pooling 1D, and then we'll need a finally a dense layer, 1 output, activation equals sigmoid. So if this seems mysterious, what this is the probability that this layer is the probability that the review is positive, so it's a sigmoid. Go ahead and get rid of that, and now we want to compile our model with the atom optimizer, a binary cross entropy loss with accuracy metrics. Not metrics, metrics equals accuracy. Okay, that's our model, and that is all we need for that. So now we are ready to think about training it. So let's go ahead and do that next. So what we want to do is train and dump the history of our training in an object that we're going to call history. Model.fit. We're going to pass train batches, 10 epochs, and we're going to need validation data, and that'll be test batches, and we'll use something like 20 validation steps. Okay, so let's scroll down a little bit so you can see it first of all, and then we're going to think about once it's done, let's go ahead and plot it. So may as well do that now. So let's handle that. So we want to convert our history to a dictionary, and that's history.history. And we want to get the accuracy by taking the accuracy key, and we want the validation accuracy using correct syntax, of course. Val accuracy for validation accuracy. And the number of epochs is just range 1 to len of accuracy plus 1. So then we want to do a plot, big size, nice and large, 12 by 9. We want to plot the epochs versus the accuracy. B0 label equals training accuracy. We want to plot the validation accuracy using just a blue line, not blue O's, or dots, blue dots, sorry, and label equals validation accuracy. Plot dot x label epochs plot dot y label accuracy. And let's go ahead and add a title while we're at it. Training and validation accuracy. Scroll down a little bit. We will include a legend. Having an extraordinarily difficult time typing tonight. Location equals lower right. And a y limit of 0.5 and 1. That should be a tuple, excuse me. And plot.show. All right, so let's go ahead and head to the terminal and run this and see what the plot looks like. And we are back. Let me move my ugly mug over so we can see a little bit more, and let us run the software and see what we get. Okay, so it has started training, and it takes around 10 to 11 seconds per epoch, so I'm just going to sit here and twiddle my thumbs for a minute and fast forward the video while we wait. So of course, once it finished running, I realize I have a typo, and that is typical. So in line 46, I spelled out plot instead of PLT, but that's all right. Let's take a look at the data we get in the terminal anyway. So you can see that the validation accuracy is around 92.5%, pretty good, and the training accuracy is around 93.82, so a little bit of overtraining, and I've run this a bunch of times, and you tend to get a little bit more overtraining. I'm kind of surprised that this final, now that I'm running it for YouTube, it is actually a little bit less overtraining, but either way, there is some evidence of overtraining, but a 90% accuracy for such a simple model isn't entirely hateful. So I'm going to go ahead and head back and correct that typo and then run it again and then show you the plot. So it is here in line 46 right there, and just make sure that nothing else looks wonky, and I believe it is all good there. Looking at my cheat sheet, everything looks fine. Okay, let's go back to the terminal and try it again. All right, once more. All right, so it has finished, and you can see that this time the validation accuracy was around 89.5%, whereas the training accuracy was 93.85. So it is a little bit overtrainy in this particular run, and there is significant run-to-run variation as you might expect. So let's take a look at the plot. All right, so I've stuck my ugly mug right here in the middle. So you can see that the training accuracy goes up over time as we would expect, and the validation accuracy generally does that, but kind of tops out about halfway through the number of epochs. So this is clearly working, and this is actually pretty cool. With such a simple model, we can get some decent review or sentiment, as it were, classification. But we can do one more neat thing, and that is to actually visualize the relationships between the words that our embedding learns. So let's head back to the code editor, and then let's write some code to tackle that task. Okay, so before we do that, I want to clean up the code first. Let's go ahead and do that. So I will leave in all that commented stuff, but let's define a few functions. We'll need a function to get our data. We'll need a function to get our model. And we'll need a function to plot data. And we'll need a function to get our embeddings. We'll say retrieve embeddings, and I'll fill in the parameters for those as we go along. So let's take this stuff from our get our data, cut that, paste it, and of course use proper indentation because Python is a little bit particular about that. Okay, make sure everything lines up nicely. And then of course we have to return the stuff that we are interested in. So we want to return train data, test data. And in fact, that's not actually what we want to do. I take it back. Let's come down here and we want our, we don't actually want to return our data, we want to return our batches. So return train batches, test batches. And we'll also need our encoder for the visualizing the relationships between words. So let's return that now. Okay, now let's handle the function for the get model next. So let's come down here and grab this. Actually, let's grab all of it and come here and do that. And let's make embedding dim a parameter of our model. And you notice in our model we need the encoder, so we also have to pass in the encoder as well as an embedding dim. And then at the bottom of the function we want to return that model. Pretty straightforward. So then let's handle the plot data next. So we have all of this. Grab that and indent here. So we're going to need a history, and that looks like all we need because we define epochs, accuracy, and validation accuracy. Okay, so it looks like all we need in the plot data function. So then we have to write our retrieve embeddings function, but first let's handle all the other stuff. We'll say train batches, test batches, and encoder equals get data. In fact, let's rename that to get batch data to be more specific. This is kind of being pedantic, but you always want to be as descriptive as possible with your naming conventions, so that way people can read the code and know precisely what it does without having to make any guesses. So if I just say get data, it isn't necessarily clear that I'm getting batches out of that data. I could just be getting single instances. It could return a generator. It is a little bit ambiguous, so changing the function name to get batch data is the appropriate thing to do. So then we'll say model equals get model, and we pass it the encoder, and then the history will work as intended, and then we call our function to plot the history, and that should work as intended as well. And now we are ready to tackle the retrieve embeddings function. So that is relatively straightforward. So what we want to do is we want to pass in the model and the encoder, and we don't want to pass. What we want to do is the purpose of this function is to take our encoder and dump it to a TSV file that we can load into a visualizer in the browser to visualize the principal component analysis of our word encodings. So we need files to write to, and we need to enumerate over the subwords in our encoder and write the metadata as well as the vectors for our encodings. So out vectors io.open vex.tsv, and in write mode an encoding of UTF-8. We need out metadata, and that's similar, meta.tsv write encoding equals UTF-8, very similar. Now we need to iterate over our encoder subwords and get the vectors out of that to dump to our vector file as well as the metadata. Weight subnum +1, and so we have the +1 here because remember that we start from 1 because 0 is for our padding, right? 0 doesn't correspond to a word, so the words start from 1 and go on. So we want to write the word plus a new line, And for the vectors, I'm going to write a tab delimited string x in vector and plus a new line character at the end. And then we want to close our files. Okay, so then we just scroll down and call our function retrieve embeddings model and encoder. Okay, so assuming I haven't made any typos, this should actually work. So I'm going to go ahead, head back to the terminal and try it again. All right, moment of truth. So it is training, so I didn't make any mistakes up until that point. 1 second, we'll see if it actually makes it through the plot. Oh, but really quick, so if you run this with TensorFlow 2, let me move my face out of the way. If you run this with TensorFlow 2, you will get this out of range end of sequence error. And if you do a Google search for that, you will see a thread about it in the GitHub, and basically someone says that it is fixed in 2.1.0.rc1, the version of TensorFlow, which I am running. However, I still get the warning on the first run. In version 2.0.0, I get the warning on every epoch, so it kind of clutters up the terminal output, but it still runs nonetheless and gets comparable accuracy, so it doesn't seem to affect the model performance, but it makes for an ugly YouTube video and gives me uneasy feelings. So I went ahead and updated to the latest release candidate 2.1.0, and you can see that it works relatively well. So 1 second and we'll see the plot again. And of course, I made a mistake again. It's plot history, not it's plot data, not plot history. Let's fix that. All right, plot. Let's change this to plot history because that is more precise. And we will try it again. Let's do it. All right, so it has finished, and you can see that the story is much the same. A little bit of overtraining on the training data. Let's take a look at the plot. And the plot is totally consistent with what we got the last time, an increasing training accuracy and a leveling off of validation accuracy. So let's go ahead and check out how these word embeddings look in the browser. But first, of course, I made a mistake. So weights are not defined, and that is because I didn't define them. So let's go back to the code editor and do that. All right, so what we want to do is this. Weights equal model.layers sub0.get weights. So this will give us the actual weights from our model, which is the 0th layer is the embedding layer, and we want to get the weights and the 0th element of that. So I'm going to go ahead and head back to the terminal, and I'm going to actually get rid of the plot here because we know that works and I'm sick of seeing it. So we will just do the model fitting and retrieve the embedding. So let's do that now. This is one of the downsides of doing code live is I make all kinds of silly mistakes while talking and typing, but that's life. See you in a minute. All right, so that finished running. Let's head to the browser and take a look at what it looks like. Okay, so can I zoom in? I can a little bit. So let's take a look at this. So to get this, you go to load over here on the left side. You can't really see my cursor, but you go to load on the left side, load your vector and metadata files, and then you want to click on this 3D labels mode here. And let's take a look at this. So you see right here on the left side, annexed, seeded, and ottoman. So these would make sense to be, pretty close together because they, you would expect those three words to be together, right? Annexed and seeded. If you annex something, someone else has to seed it. It makes sense. Let's kind of move around a little bit. See what else we can find. Okay, so this looks like a good one. We see waterways, navigable, humid, rainfall, petroleum, earthquake. So you can see there are some pretty good relationships here between the words. That all makes sense. If you scroll over here, what's interesting is you see Estonia, Herzegovina, Slovakia, sorry for mispronouncing that, Cyprus. You see a bunch of country names, so it seems to learn the names. It seems to learn that there are relationships between different geographic regions, in this case countries. There we see ceded and annexed on Ottoman again. And you can even see conquered in here next to annexed and ceded. Deposed, archbishop, bishop assassinated. Oh, you can't see that. Let me move my face. There, just move me over. So now you can see surrendered, conquered, Spain, right? Spain was conquered for a time by the Moors. Archbishop deposed, surrendered, assassinated, invaded. You can see all kinds of cool stuff here. So this is what it looks like. I've seen other words like beautiful, wonderful together, other stuff. So if you play around with this, you'll see all sorts of interesting relationships between words. And this is just the visual representation of what the word embeddings look like in a reduced dimensional representation of its higher dimensional space. So I hope that has been helpful. I thought this was a really cool project. Just a few dozen lines of code and you get to something that is actually a really neat, kind of a neat result where you have a higher dimensional space that gives you mathematical relationships between words, and it does a pretty good job of learning the relationships between those words. Now what's interesting is I wonder how well this can be generalized to other stuff. So if we feed it, you know, say Twitter, tweets, could we get the sentiment out of that? I'm not entirely sure. That's something we would have to play around with. It seems like you would be able to, so long as there is significant overlap in the dictionaries between the words that we have for the IMDb reviews and the dictionary of words from the Twitter feeds that we scrape. But that would be an interesting application of this to kind of find toxic Twitter comments and the like. But I hope this was helpful. Just a reminder, my new course is on sale for $9.99 for the next 5 days. There will be one more sale last several days of the year, but there will be a gap of several days in between. This channel is totally supported by ad revenue as well as my course sales. So if you want to support the cause, go ahead and click the link in the pinned comment / description. And if not, hey, go ahead and share this because that is totally free. And I like that just as well. Leave a comment down below. Hit the subscribe button if you haven't already. Hit the bell icon to get notified when I release new content. And I will see you in the next video.